Alright, hi guys. Welcome to a quick live stream. This is just for my grade 9s. They want to go through a worksheet I gave them for a test that they've got tomorrow. So it's all about heat energy transfer. So it's relevant if you're doing IGCSE Physics and just looking at some problems involving specific heat capacity and latent heat. So like the latent heat of fusion of ice or vaporization of water, etc. So it's all relevant if you're doing IGCSE. Okay, so I'm just going to go through the problems and then hopefully it makes sense for them. Okay, so let me move it up here. Okay, so the first problem was suppose a piece of iron with a mass of 12.5 grams at a temperature of 100 degrees is dropped into an insulated container of water. The mass of the water is 132 grams. The temperature before adding the iron is 20 degrees C. What's the final temperature of the system going to be? And then the specific heat capacity of iron is 450 joules per kilogram per degree. So the first thing what you've got to think about is no energy is really being lost in the system. The energy is simply going from the iron to the water. So what you can say is, well, because no energy in this whole as the whole is being lost or gained, you can say, well, 0 is equal to the mass of the iron times the specific heat capacity of the iron times by the change in temperature of the iron, which is going from 100 degrees down to some temperature, plus the mass of the water times the specific heat capacity of the water times by the change in temperature of the water. So what's going to happen is the iron will reduce its energy, the water will gain the energy that the iron lost, and then somewhere in the middle they're going to meet, and then that's how we're going to find out what our final temperature is. So if you put all these numbers in, okay, it looks complicated to begin with. You've got a lot of brackets there. So firstly, I would kind of sort out these things to begin with here. So you've got 0.0215 times 450. Well, if you times it by 450, you get this here, 9.675. And also here you've got 0.132. Now, why am I saying 0.132? It's because the mass of the water is in 132 grams, but our specific heat capacity we know in kilograms, okay? Anyone wants to say hello? Anyone on the live chat? Don't forget to say hi. Okay, so you work through, okay, and then you find that the final temperature is 21.4 degrees. All right, okay, the next one. So now we've got a 12.48 gram sample of an unknown metal. It's heated to 99 degrees. It was plunged into 50 grams of 25 degree water. The temperature of the water rose to 28.1 degrees, assuming no loss of the energy in the surroundings. How many joules of energy did the water absorb? So, okay, so this is quite nice really, because all you need to do is use the specific heat capacity problem. So you can see delta Q equals MC delta T, okay? You know the mass of the water, it's 50 grams. You know the specific heat capacity, and then the change in temperature. Well, remember it's final minus the initial. So the final temperature was 28.1. The initial temperature was 25. Okay, and you get 651 joules. So how many joules of energy did the metal lose? Well, it's exactly the same. The energy the water gained is equal to the energy the metal lost. And then finally it says, what is the specific heat capacity of the metal? Well, this time, the delta Q is actually negative because the energy came out of the metal. Okay, so the energy came out of the metal. We know the mass of the metal. The change in temperature. Well, the final temperature was 28.1, and the initial temperature was 99. So you're going to say, well, delta T is 28.1 minus 99. And okay, so you end up with like a negative number here, and you've got a negative number on the other side. So it's not a big deal, because when you divide one from the other, we get a specific heat capacity of 735.7 joules per kilogram per degree. PS guys, if I've made a mistake, I do apologize. It is possible I might have made a slip. And in fact, it'd be great if you could tell me. But if I've made a little slip, just let me know. Okay, next one. No one's going to say hi. No one on the live chat at all. Okay. Okay, the next one. Okay, we've got a 440 gram block of an unknown metal at 90 degrees C. It's dropped into an insulated vessel containing 60 grams of ice at 0 degrees. After the system has reached an equilibrium, it was determined that the ice had melted and the water that was left is now 10 degrees. So what's the specific heat capacity of the metal? Well, two things have happened, okay? So firstly, we needed energy just to convert the ice into water at 0 degrees, and then finally raise the temperature from 0 degrees to 10 degrees of the water. So first you need to think about the latent heat of fusion of ice. So we're converting from ice to water, okay? So this is what we're going to use. Delta Q equals ml. So 0.06 is the mass of our ice, times by the latent heat of fusion of ice, which is 3.34 times 10 to the 5. So just to convert the ice into water, we need 20,040 joules. So that's just the energy needed to convert the ice to the water. Then we're going to increase the temperature. Okay, so now we're going to use our delta Q equals mc delta T. Okay. We're going to put the values in, and again we get the same mass of the ice is the same mass of as the water. So we've got 0.06 times by the specific heat capacity of the water, and then the change in temperature. Well, the final temperature was 10 degrees, so 10 minus 0, and we get 2,520 joules. Okay, so two things have happened. Number one, we use the energy to increase the temperature. We use the energy to convert the ice into water. Then the new water that we'd made from the ice, we then need energy to increase the temperature as well. So the total energy that's lost by the metal is the addition of these two things. So it's 20,040 plus 2,520. So the total energy that we need, or that's come from our metal, is 22,560 joules. Okay, then what's the point of this? We're trying to find the specific heat capacity of the metal. So delta Q equals mc delta T. Again, I've said it's negative. The reason why I've said it's negative is because our metal has lost the energy. Okay, so it's losing the energy. It has left. Okay, so there's the mass. Remember, it was 440 grams, which is 0.44 kilograms, times by its specific heat capacity. Excuse me. Then the change in temperature, well, it went from 90 to 10, so it's the final minus initial conditions, so 10 minus 90. Okay, work that all and then out, and then you get a specific heat capacity for the metal, which is 641 joules per kilogram per degree, hopefully. Okay, the next one. A 35 gram block of metal at 80 degrees. Hi there. Arslan Khan, how are you doing? I hope you're doing well. I hope this is helping you with your IGCSE physics, if you're doing IGCSE physics and thermal properties. Okay, let me just go over question number 4. So a 35 gram block of a metal at 80 degrees is added to a mixture of 100 grams of water and 15 grams of ice at 0 degrees in an isolated container. All of the ice melts and the temperature in the container rose to 10 degrees. So what is the specific heat capacity of the metal? Well, what we need to think about is, first, we need energy to convert the ice to water and then raise the temperature of the water to 10 degrees. So firstly, we've only got 15 grams of ice, okay? So we're going to use delta Q equals ml. So we've got 0.015 kilograms times by the latent heat of fusion of ice, which is 3.34 times 10 to the 5, okay? And we get the energy needed just to convert the ice to the water is 5,010 joules. Now, that ice, that 15 grams of ice, we now need to add to the total mass of the water. So we've got 15 grams of water. We've also converted 15 grams of ice into water. So we've now got 0.115 kilograms of water that we're going to raise the temperature. So now we just times 0.115 times 4,200. And then what's the change in temperature is 10. Okay, 10 minus 0. Okay, then we get 4,830 joules just to raise the temperature up. So the total energy that we need is 5,010 plus 4,830, which gives us 9,840 joules. So that's how much energy that we gained from the block of metal. Okay. Now we want to work out finally, well, the whole point of this was working out what's the specific heat capacity of the metal. So delta Q equals MC delta T. That energy is negative, okay? The reason why it's negative is because it's leaving the metal, okay? And then that kind of makes sense because we're going to have a negative temperature change here as well. So we've got minus 9840 is equal to 0.035 times by the specific heat capacity of the metal, and then times by the delta T, the change in temperature, which is minus 70. It went from 80 to 10. And we find that the specific heat capacity of the metal is 4,016 joules per kilogram per degree. Okay, number 5. Okay, a student heats a piece of 130 grams of an unknown greyish metal to a temperature of 99.2 degrees. She places the metal in a styrofoam cup that contains 55.7 grams of water at a temperature of 23.0 degrees. Okay, the hot metal heats the water in the cup to 31.4 degrees. Calculate the specific heat capacity of the metal. Well, the energy gained by the water is equal to the energy lost by the metal. So we can say delta Q equals MC delta T. Okay, so the mass of the metal is 0.0557. Oh no, hang on, wait, sorry, that's the mass of the water, sorry, 0.0557 kilograms times by the specific heat capacity of the water, which is 4,200. And then the change in temperature here, well, we went from 23 degrees to 31.4 degrees. Okay, so we work all this out and we get 1,965.096 joules. Okay, great. Okay, I haven't done anything with significant figures yet. I'm just doing all my raw calculations first. Now, that's the energy that the water gained, which is going to equal, in theory, the energy that the metal loses. Okay. Now, again, we're going to use delta Q equals MC delta T. This time, I'm saying, again, it's a negative value because the metal has lost the energy. So this is the mass of the metal, which is in kilograms, 0.13, times by the specific heat capacity, times by our delta T. And remember, this time we went from a temperature of 99.2 degrees down to 31.4 degrees, okay? And then finally, the only thing we don't know is C. So if you rearrange this, we get 222.95 degrees, and then just making it to 3 significant figures, we get 223 joules per kilogram per degree. Ghost 1808, hi, how are you doing? Hope you're doing well. Okay, I'm just going through some heat problems, additional heat energy problems, just for my grade 9s, because they've got a test tomorrow, so I thought I'd quickly just go through some problems for them. Okay, but glad you can join us. Okay, number 6, how much heat energy is required to change 3.5 kilograms of ice that's at 0 degrees C into water at 20 degrees? Okay, so there's 2 stages to this problem. So the first stage is we're going to change the ice into water, and the second stage is we're going to raise the temperature of the water. Okay, so firstly we're going to use delta Q equals ml, okay, using the latent heat of fusion of ice, okay, value. So we know we've got 3.5 kilograms of ice. That's the latent heat of fusion of ice. So the energy needed just to convert 1 kilogram from ice to water. And we find that we get a whopping, well, what is this? 1,169,000 joules to change from ice into water. And that's still at 0 degrees, okay? Now, what we need to do is, again, now we need to raise the temperature from 0 to 20 degrees. So delta Q equals MC delta T. So we've got 3.5 kilograms times by the specific heat capacity of water, which is 4,200, times by 20. And we get 294,000 joules. Okay, now, so there's two things. So that was our raising the temperature up from 0 to 20. And we also converted our ice into water. So we need to add these two energies up together. So we get our final total amount of energy, and that is 1,463,000 joules is our final answer. Okay, and then our last problem here, number 7. Okay, and just need to move it so I can see it better. Okay, 0.1 kilograms of ice at 0 degrees is dropped into 1 kilogram of water at 18 degrees. What's the final temperature of the mixture? So we need to do two things. The energy, we need to we need energy to change the ice into water, and then we need to raise the temperature of the cold water. So we're going to have as the whole system, there's not going to be an energy change. Okay, so we can say 0 is equal to the energy required to change the ice into liquid. Okay, then we're going to raise the temperature of that liquid from 0 to a new temperature, which we don't know. But also, we're going to take energy from our hot water, so our hot water will actually reduce in temperature. Okay, so first things first, let's convert the ice into water, which is this one here. So we've got 0.1 excuse me, 0.1 times 3.34 times 10 to the 5. So that is just converting our ice into water. Then now that we've made our water, we need to raise the temperature of that water. So the temperature change is we're going up to a temperature of T. Okay. And remember, it was ice water, so we know it's going from 0. So that's the final temperature minus the initial. Okay. We also have 1 kilogram of hot water that was at 18 degrees, and that's going to be reduced to T. Okay. And again, we don't know what T is, but it's the only thing we don't know. Okay. Next thing we need to do with all this is tidy it up a little bit. So I would just, you see all these things like multiply, let's just tidy it up. So I've got 3.34 times 10 to the 5, well, times by 0.1, and that becomes 3.34 times 10 to the 4. Okay, here, okay, in this brackets here, well, I've got 0.1 times 4,200 times by T. Well, that's just going to be 420 times by T. And then the next thing is just times by 0, so that doesn't really do anything. Then I've got 1 times 4,200 times by T, so that's just 4,200 T here. And then minus 18, so 4,200 times minus 18 is this 75,600. Okay, so next we need to just add up all these numbers here. So I did the hi Daniel, Ken. Okay, yeah, hi sir, how are you doing? Are you going to be doing these live streams closer to the IGCSE mocks and the finals? That'd be really cool. Daniel, yeah, I'm definitely thinking about doing that. I had the idea of doing like live streams probably like the night before, or maybe like a couple of nights just leading up to the exam. Then the idea is people can like kind of ask me like any problems that they've got. Okay, Daniel. Okay, so these two values here, this minus this, you end up with a negative. But when I work out what that is, I can put it over here, and I get 42,200. I've already got this 4,620 T here. I divide this the 42,200 by 4,620, and I get my final temperature is 9.1 degrees. Okay, I think I'm done. Okay. Hi Tina. Okay, in question 7, where do you get the ml? Okay, where do you get the ml? Do you see here you've got 0.1 kilograms of ice? Well, what you need to do is you need to convert the ice into water. So we need to use the specific heat capacity of, sorry, not the specific heat capacity, the latent heat of fusion of ice to convert the mass of the ice into water. There we go. Okay. Vernon Hugo, thank you, sir, for the IGCSE streams in the future. Yeah, definitely. Okay. Okay, that's okay, that's great. Okay, so I'm glad that's going to help. Okay, guys, I think I'm kind of done. Anything else anyone wants me to go through? So if you didn't get any of that, then well, you just have to go back through the video. Okay, guys, I'm done.